Hello everyone, can you hear me? Awesome. Perfect. So, very good morning to all of you. I believe all of you had a good session in the quiz one, and was there any challenging questions, or all of you were good there? Did it go well? Anybody found it challenging or too easy? Okay, so I see no comments about quiz one. I believe you all enjoyed it. So let's wait another 2 minutes for others to join, and then let's start the lecture. I thought it was a little tough. Okay, Thomas, in that case, you need to practice more for the midterm. Like, midterm will be slightly difficult than quiz one. And because the timing wise, I provided more time than usual, because if it was a paper-based exam, it will be 50 minutes and closed book. At the same time, it will have 30% more questions. But in this case, I reduced 30% of questions from the original exam, and then I bumped up the time to 90 minutes instead of 50 minutes due to the online environment setup. So be ready for the midterm. That will be a little more challenging if you do not practice. Now, midterm is not only 50 minutes, midterm is 2 hours, but it will be more challenging. You have to practice more. Okay. The thing about this closed book and open book exams that I find throughout the years is when it is open book, students if students think that it's very easy, so that you can browse internet, you can do whatever, and the only thing that they forget is the timing is of essence, right? So if you are familiar with the theories and if you are familiar with the concepts and everything, then it's easy to answer. Then it will take a very less amount of time. But if you use all the sources and you don't know where to look into, then it will take more time and it might look more challenging. Yeah, Alexandra, you are right. So if it is on the saturated line, we'll call it two-phase region. Like in the exam situation, you can just call it saturated vapor in two-phase region or whatsoever, because like it will be the TAs and myself who are looking at the answer, so we know what you are meaning. Did I answer you, Alexandra? Okay. How did the midterm will be more difficult than quiz? Because the questions will require you to like answer the questions in the midterm will be required to be answered in a faster manner, because you have questions for 2 hours. You had almost like 1.5 hours for a lower amount of questions. So that's why you need to practice your theory and you should be familiar. If you are familiar, then it should not be a problem, because even the midterm is like about 70% of the questions that I used to give on a paper-based exam in a closed book format. I'm just reducing these questions and expanding time just to give you more accommodations as it is in the online environment. Okay. will the format of the midterm similar to the quiz? Yes, it will be similar, and there's a what mock midterm exam posted in the under the modules the second week, and if you go there you can find the paper-based version of the midterm mock midterm, and then I have posted a mock midterm question in quiz 1. These are just to familiarize yourself with the expectations and what is the format of the quiz, right? So if you go to the quiz, that is not the whole exam, I mean the Canvas quiz. So it will give you an idea, okay, what we'll be seeing in the midterm, like the format wise, right? You are supposed to put your answers in each box, and then you're supposed to scan, the answers and upload the PDF, right? So I will go into these details in the coming slides. So let's start the question. I see a lot of questions about midterm. We'll discuss this thing in the coming slides, okay? Okay, so today we are going to start lecture 7 of our APSC 252 thermodynamics course, and there today we'll learn the first law of thermodynamics, enthalpy. Enthalpy we have not discussed earlier, and now today we'll discuss that one, and constant pressure specific heat. Okay, so by the end of this lecture you will be able to apply the first law of thermodynamics for closed systems. So we learned the basics of first law when we try to apply it to the closed systems. Today we will practice it further, right? And you will be able to calculate the enthalpy by using the thermodynamic tables and constant pressure specific heat. So you remember, for internal energy we had two ways of calculating internal energy. One is by the tables, the other one is by using the constant volume specific heat. Similar to that, we'll see how we can calculate the enthalpy as well, right? So if you want further information, or if you want to broaden your knowledge, you can read from chapter 3.9 to 3.11 of the recommended text. Okay, here are some information that you were looking for about the midterm. So this 60-minute, I will increase 60 minutes time frame. This is the number that I originally planned, but hopefully I'll increase it. And midterm exam, 35% of the total final grade. And as I mentioned earlier, there's a mock exam uploaded for a paper-based exam. And then one question was uploaded in the Canvas quiz format, right? So that you can go there and practice yourselves. And please make sure that you have a PDF scanner, like to scan your answers, right? This exam is not like the previous one, right? Sorry, give me 1 second. 29th. Okay, sorry, my bad. It should be rectified as 28th. Sorry, this is not. It's on Friday, definitely. This one is wrong, and 28th, right? So then you have to keep a PDF scanner, and when you are doing the mock question in the Canvas, you can use the PDF scanner and scan your workings and upload it there, so that you know the process beforehand. Otherwise, don't wait until the last moment and until the exam to test your technology. That will keep you that will get you into trouble, right? So this exam will contain the contents that we learn from lecture 1 to 7. That means today is the last lecture that you are going to be participating before the midterm. So you will have 2 consecutive tutorial sessions on Tuesday and Wednesday, so that you can practice your theory and you can ask your questions about the theory, so that you are well prepared for the midterm. And you have all perfectly 1 week to practice for the midterm. And while you're practicing, I recommend you to complete the questions in assignment 1 and 2, and also tutorial 1 and 2, right? And yes, there's a like the scan has to be uploaded before the time ends. How many questions in the midterm? I cannot remember it exactly, but in the announcement that I'm going to make, maybe I'll be able to answer that one. Okay. We don't have any lecture on Monday because it's a public holiday, so you will have a free time. You will have more free time to practice. Okay. So here are some main topics that we'll be testing in the midterm: thermodynamic properties, phase diagrams and tables, and thermodynamic processes, like polytropic process, isothermal process, isobaric process, and kind of stuff, and ideal gas law, and when and where to use it. And please don't use ideal gas law if you see water in this course. I'm telling you, like, I'm not going to test you on using ideal gas law on water. Okay, so please don't use that. That is a common mistake I see everywhere. And please don't use ideal gas law on liquids, right? It is only for gases. It's as the name implies. So I emphasize this one because there's so many students mistake this aspect and then lose a lot of marks. So I don't want to see that. And specific heat, like constant volume specific heat and constant pressure specific heat, will be needed for this exam. So you already know what is constant volume specific heat, and today we'll learn constant pressure specific heat. And then internal energy, heat, work, and the first law, right? So if you know all these and the contents from lecture 1 to 7, so you are ready for the midterm, right? Any questions regarding the midterm? Yeah, you can write your answer on iPad and then you can save it as a PDF and then you can upload it as well. That's fine. If you're writing on paper, then you can keep a PDF scanner ready in your mobile phone, right? Okay. So, Mena, I believe I answered. The level of difficulty on the midterm will be uh, higher than the quiz one. So, if you are practice, I mean, I'm not purposely making it difficult or whatsoever. I just warn you, like, so that you practice further and you can complete the questions in a shorter time. You know what I mean? So there will be more contents to be covered in the given time. That's what I said. Okay, don't panic. I don't want you to like not score. As your professor, I want you to score and excel in this exam. And I'm not kind of the person that set up the exams that nobody can score 100. I want you to score 100. So don't be panicked or don't be paranoid. So I'm not going to try and trick you, but I'm just warning you so that you can practice, Okay. Right. And here, now back to this lecture. So we have a new parameter, enthalpy. You remember in the past lectures, we learned a new parameter called internal energy, right? And enthalpy, internal energy is the energy that is stored in a given substance as internal energy. And then in addition to internal energy, when it comes to enthalpy, we have internal energy plus PV, and we call this PV the flow work, right? So you have still not learned what is flow work and why do we need flow work in enthalpy, and all these questions. I know all these things should be coming up to your mind right now, but we have not learned it so far. But what I want you all to know at this point is enthalpy is internal energy plus pressure into volume. So the total enthalpy is equal to total internal energy plus pressure into total volume of a given substance. And then similar to all other parameters that we learned so far, if you divide the entire equation by the mass, you get the specific enthalpy, and then specific enthalpy is equal to specific internal energy plus pressure into specific volume, right? The unit of this one is going to be in, like here, in kilojoules, and then here it is going to be in kilojoules per kilogram, right? So now you can see this has the energy, like this has the units for energy, right? Joules. So this is form of an energy, like this is the total energy that is uh, available in a given substance. Okay, and apart from the flow work, do you find anything that is not clear in this definition? Are we all good? Perfect. So now for a closed system, we wrote the first law equation as total energy is equal to the total specific energy into mass, which is written as total internal energy plus kinetic energy plus potential energy, or we can write it as this form, right? This part is the specific form of each energy component. Do we have any questions about that one? Okay, so now when it comes to open systems, it's slightly different. In open systems, what we have is, in addition to what we have in the first equation, is this flow work component, right? So we have this flow work component, and with that, if we have some parameter that combining these two, that is easy for us, right? If we were to calculate these things manually over and over again, then that is one additional step. But if we can directly search for the enthalpy from the tables, then it is much easier than finding the internal energy and specific volume and pressure and everything, and then calculating this component, right? That is why we have this new parameter, which is used in open systems mostly, right? It can be used in closed systems, but it is very important in open systems, right? And as of now, don't worry about the open system equation. What I wanted to do is, I wanted you to know that is why we have enthalpy in this discussion. That is where we need it, the application of this one, right? Uh, so determine the specific enthalpy from thermodynamic tables is very similar to what we did with internal energy and specific volume. Basically, you are going to use the same set of tables, and when you go there, now you see there's, in the compressed liquid tables, we have this enthalpy column, right? So it is nothing different than finding internal energy, which is right next to it, and also it is nothing different than finding specific volume right next to it, right? So if you have the temperature and if you have the pressure, you check the temperature, you check the pressure, and then you grab whatever the required enthalpy, right? It's the same with superheated vapor as well. And then there, if you have 100 Celsius as your temperature, and if you have 10 kilopascal as your pressure, then your enthalpy is going to be this one, right? So now you can see finding this property from superheated tables or compressed liquid tables is nothing different, and it's the same for two-phase region as well. So basically, if it is water, we have pressure and temperature entry tables. So we use the same usual procedure that we followed to find our internal energy and specific volume, right? Enthalpy is no different in the sense of identifying the values from tables. Now, for internal energy, we develop these two relationships, right? And what we see down here is the very same relationships apply for the enthalpy as well. So if you want to find the quality of a mixture, can you use enthalpy instead of specific volume or internal energy? Can you do that? Yes, definitely you can, because these relationships are the ones that we used to find the quality and to find the states when the quality is available and all that, right? Therefore, so wherever you used quality, you can use the same relationships to calculate the average enthalpy of a given system, or else if the enthalpies are given, then you can find the quality of the system using those enthalpies. So this brings up another point. Can we use enthalpy? Can we use enthalpy to check whether a substance is in superheated region or two-phase region or in compressed region? Can you do that? Yes, you can, right? So if you take this one, so let's say this is a PV diagram and we have a dome and this is HF and this is HG, and if our given H is between these two values, then we know that it is in two-phase region. If our H value is larger than or higher than Hg, then we know that it is in superheated region. If our H value is lower than Hf, then we know that it is in compressed liquid region. And then there's another question. Can we assume for a given temperature, let's say, let me draw an isothermal line. Okay, so this is an isothermal line, right? Now for a given temperature, right, let's say this is T equals 20 Celsius, right? So T equals 20 Celsius. For a given temperature, can we get the enthalpy value at this pressure? Let's say maybe 2000 kilopascals. Now this is in compressed liquid region, right? So if it is in compressed liquid region, you know that for some substances, we don't have comprehensive set of compressed liquid tables. So in that case, can we assume this value to be equal to enthalpy at this point, enthalpy at point 1, right? This is point 1, to be equal to enthalpy at point 2. Can we do that? We can, right? So now it brings us to an interesting point where we were able to find VF, UF. We were able to use VF, UF, and HF to represent the property values in the compressed liquid region at a given temperature. Are we all clear? Perfect. Now moving on. Here's the next new parameter that we are going to introduce ourselves into today. So if you read the definition, it says, what is constant pressure specific heat? It is the energy required to raise the temperature of a unit mass by 1 degree in a constant pressure process, right? So in the previous definition, to find constant volume specific heat, this is the setup we used, right? Our goal was to have a setup which is constant volume, and then we put one or unit substance inside there, and then we try to increase the temperature by 1 Celsius, and then we calculated or we measured the energy needed to increase that temperature, right? So that was called constant volume specific heat. And for another substance, for the same substance, if we want to find constant pressure specific heat, then we have to develop a constant pressure setup, right? In which the pressure does not go higher. So if we have a piston cylinder mechanism with no friction involved, then the pressure is going to be the same value throughout the process, right? So we provide heat and we put 1 kilogram of the substance inside this chamber, and we provide heat, and then we provide heat until we see 1 Celsius temperature difference, right? And then the amount of energy that we applied or we inserted into this chamber is going to be called as Cp. So are we clear about the definition of Cp? How do we calculate that one, and what is the meaning of that? Perfect. So as you all know, Cv was recognized as a property of a substance, right? And it goes similarly for the Cp. It is also a property of a given substance. So what does that mean? Why it is important to know this fact? Then we can say that they are independent of the processes that a system is undergoing, right? And there's another interesting characteristic. Cp is always higher than Cv, you see here, right? And why is that? Don't question me yet. We'll be deriving this one, like we'll be proving why it is like that using ideal gas assumptions, and then you will see why Cp is always greater than Cv. Okay, and Cv and Cp can be used to calculate U and H, right? You remember you had a relationship between Cv and internal energy in the previous lecture, right? In the previous lecture, this arrow could be confusing. Let me erase this one. This arrow is not relevant now, right? You had a relationship. Now in this slide you see another relationship which connects Cp with the enthalpy. Why knowing this relationship is important? Because we may want to use this relationship to calculate the enthalpy difference at a given during a given process when we don't have property tables, right? Are we clear? So anybody feeling that we are going too fast or too slow, or the phase is good? Any ideas? Are we going good? I mean, okay, perfect. All right. So solids, and when it comes to solids and liquids, they are nearly incompressible, right? Therefore, when there's no compressibility is involved, then we can say that dH and du equals C dt, right? Roughly equals. So what does this mean? Then Cv and Cp becomes one value for solids and liquids, right? This is one confusion some students had throughout the years, like why do we have Cv and Cp? Because we used to know specific heat as one parameter during our school time, and we used mc theta all the time. We never had to worry about Cp or Cv because you were applying those equations to liquids or solids, right? When it comes to gas phase or vapor phase, then only we have these two different parameters: constant volume specific heat and constant pressure specific heat. Because the gases are not incompressible, they are compressible, right? They change their volume significantly. Therefore, in those cases, Cp and Cv are not equal to each other. But when it comes to liquid and solids, then those are equal to each other, right? So when those are equal to each other by the two definitions we had earlier, so you can write Cp equals dH by dt, or partial derivative of enthalpy by temperature. So, or then you can say Cv equals du by dt. And from these two equations, we can say if this is equal to C, if both of these are equal to C, then we can say that this relationship is true that we see here, right? And then in this case, we can do an approximation if we know an average specific heat value for a given substance during a given temperature range, then we can use this equation to calculate the enthalpy difference or internal energy difference of a solid or a liquid, right? And the same goes for gases, but there you will have to consider whether you are going to use Cp or Cv depending on the parameter that you want to find, whether it's enthalpy or internal energy, right? Anything not clear? Anything not clear? Okay, so before moving forward, I want to draw something. So just for clarity, just to make sure that we all are in same page, Cp, temperature. So in a given process, we can have a variation for Cp against other parameters like this, like temperature. Like it is not always a constant, right? So don't get into that false realization. Like it is not going to be like this over the temperatures. It's going to vary. If we want to use this equation, what we are using here is an average specific heat, right? Cp, Cv, or even for solids, these variations are there. Like it could have any shape of variation, right? Do I make sense? Okay. Now we'll derive why we said the Cp is always greater than Cv, right? And there's another thing, the relationship between Cp and Cv. So if you know Cp of a given substance, then you can find Cv using this relationship. Let's see how we can do it, right? So you know that when we are when we were defining enthalpy, we use this relationship H equals U plus PV, right? So are we all in agreement about this one? This is what we learned so far, right? And then for an ideal gas, we know that PV equals RT, right? For an ideal gas, we know that this is the ideal gas equation. So if you substitute for PV using RT, then you can get your enthalpy to be this, right? So the entire relationship is given as a temperature function. R is a constant and U is only dependent on temperature. So now it's a temperature function, okay? And we know that Cv is equal to du by dt, the relationship between constant volume specific heat and internal energy with respect to the temperature, right? This is what we learned in the previous lecture. And in this lecture, we learned that Cp is equal to dH by dt, right? So then, how do we come to this relationship? What we do is we take equation 1, let's call this equation 1, and then we take equation 1 and differentiate it by temperature, right? So if we differentiate equation 1 by temperature, what we are going to get is the left hand side dH by dt. The right hand side, the first term is internal energy term, then we are going to get du by dt, right? Plus, and the second term, R is a constant, therefore it's not going to vary with temperature. Then assuming that, we can get to differentiate temperature only. When we differentiate temperature by temperature, then we get 1. So basically we are left with here, right? So if we substitute for dH and du by these definitions, then we end up coming to this final answer, right? So I just showed you the derivation so that it makes more sense, because usually I am very good at remembering things when I have a logic behind it. So if you do not understand the derivations or differentials whatsoever, so don't bother about that, because I'm not going to test you on derivations of this one, right? So, but in case if I test it, can you do that? Any challenge? Anybody who does not understand it? Perfect. So if you can remember it, this is really neat, because like this is a simple derivation. So keep that in mind. It will be handy sometime, right? When somebody asks why CP is always greater than CV, then you just have to remember, okay, CP is related to enthalpy, CV is related to internal energy. Then if I differentiate one of these definitions, then I should be able to come at the derivation, conclusion, right? So down in the road, after 10 years, if you encounter this one, then you know the logic, right? Okay, moving on. Oh, before moving on, you can see that CP with temperature, right? CP divided by R. So it doesn't really make much of a difference. R is a constant, but you can see that there's a variation, right? As I mentioned earlier in the slide. So these are not constant values. So it's going to be a function of temperature, CP, right? These are not constants. Okay, so calculating delta U and delta H, internal energy difference and enthalpy difference in any process. What are we going to do? The first thing, as always, we would prefer to go with thermodynamic tables, right? If we have thermodynamic tables, that is what we are going to do. So unless specifically asked in the question, right? So in practical life, so if we have thermodynamic tables, that's what we are going to do. That is the most accurate, right? Or else, so you can use the relationships that we just learned. Let's say if you want to find internal energy, and then you have a curve like this there, what does this area underneath this curve mean? What does this area represent? Any idea? It is the internal energy difference, right? Delta U. Excellent, Lisa. So this is what you see here. So basically, in order to calculate CV into dt, or the integral from T1 to T2, what we can do is we can get CV, a function for CV along this curve. If we know the function, then we can integrate, right? But in this course, we are not asking you to do that, because we are not going to know these functions very easily, and at the same time, the integration and everything, we do not require you to do that at this point, right? So what we are going to do, we are going to assume an average specific heat, like in this case, uh, specific heat at constant volume, right? There, if we were to find the internal energy using this CP, CV, and temperature relationship, this is the equation that we are going to use for internal energy, the bottom left-hand corner, right? So there, the CV value you see here is the average. This is CV average. Are we clear? So in our course, what we are going to do is we are going to get the average and then calculate this area instead of going for the function. Any questions, or are we super clear on what's going on? Are you still thinking, or what? It would be really nice if you can be engaged, because it's very hard, right? I can just keep on going, then sometimes some of you may feel left behind. Perfect. Now, yeah, yeah. So option 2 is not less accurate, but option 3 we consider an average, right? Therefore, it is possibly less accurate. But whenever we see this 1, 2, 3, right? So like now, as engineers, we want the highest possible accuracy, right? In our minds, we want it to be precise all the time, right? So, but the thing is, when it comes to calculations, sometimes the accuracy of one thing is not most significant, right? Like for an example, one of my professors used to say that engineers are risk averse people, right? So we design a bridge to 3 decimal points. We calculate the stresses, we calculate the strength and everything for 3 decimal points, and then we multiply it by 3, just to be just to add safety factors, right? Just to be safe. And if somebody asks why is that, just in case we don't want to take a risk, right? So sometimes if we already multiply it by 3, then calculating it to 3 decimal points may not make sense in a practical point of view, right? So like that's why we, as engineers, when we go out there, like we need to have a sense of what is significant and what is not significant when you are doing a calculation. So otherwise you will be wasting your energy and maybe a processor power if you are doing a algorithm or something to do the same thing. So yeah, so that's just something I learned down in the road, and some wise words from a wise professor. Okay, and all good with this slide. Now moving on, right? So now we learned that Cp can be written as this for ideal gases, right? For real gases, you cannot write Cp equals Cv plus R, right? For an ideal gas, there's another important parameter, very important, specific heat ratio. Specific heat ratio can be represented by K, or you might see gamma down in the road, right? K or gamma may be used to indicate specific heat ratio, but either ways, the definition is the same, Cp divided by Cv. So it could be Cp divided by Cv at a given temperature, or it could be the average Cp divided by average Cv. So it could be either ways. Whatever it is, what can we say about the magnitude of this K or gamma value, specific heat ratio, this one? Is it greater than 1 or equal to 1 or less than 1? Can you comment for an ideal gas? Is it going to be greater than 1, less than 1, or equal to 1? So I will write greater than 1, equal to 1, less than 1, right? It is always greater than 1, right? Because why? We derive this relationship, right? As you can see right up here, Cp divided by Cv, if you divide this first equation, equation 1 by Cv, then in your left hand side you are left with Cp divided by Cv, and in your right hand side it has 1 plus R divided by Cv. So R and Cv both are positive uh, components, therefore positive numbers, therefore it's going to be a positive value. Basically, then it's going to be always higher than 1, right? For an ideal gas. Okay. Now, based on this definition and equation 1 and 2, right? Using equation 1 and 2, I want you all to try deriving equations that you see inside this box. So basically, using gamma or using K, the specific heat ratio, either ways, it's the same idea. So using this new parameter, you can define specific heat and specific constant pressure specific heat and constant volume specific heat, right? So try whether you can derive this at home, right? Okay. And any questions so far? Any questions so far? Perfect. Now, to summarize the solution strategy that we discussed earlier in the previous lecture as well. So this is what I would do when I have a problem in my hand, right? So I would try to sketch the physical system. If I have a piston cylinder mechanism, then I will try to draw it, right? And then I will try to find the proper system boundary, the control mass for a closed system. Why is that? You remember the example that we used in the previous lecture. Depending on the boundary, things might look like heat or work, or maybe no work transfer, because like everything is inside, right? So depending on what we are doing, then the system boundary is very important. And then indicate heat and work transfer in and out of the control mass, right? So marking the heat and work flows will enable you to see the complete picture of the problem. And then mark the signs, very important. So if it is coming inside, let's say 10 kilojoules of heat is coming inside the system, then it is positive. 10 kilojoules, 5 kilojoules of work leaving the system, then any heat leaving is negative. And work 5 kilojoules of work done by the system, then that is positive, even though that is going out of the energy is going out of the system in that particular instance. When the work is done by the system, then it is positive, right? When the work is done on the system, negative. Likewise, so mark everything. That is step 2. I mean, these are not hard and fast rules, just to give you some guidelines so that you can have a process in your mind to start with, right? So then identify the processes, the special things about the process that is discussed, whether it's isobaric, isothermal, or whether it's a polytropic process, adiabatic process. So some relationships which we can learn about the process more, right? If there it is mentioned, please take note of that. And then list the known states and unknown states, right? So if we list down, okay, we have been provided with pressure and temperature, and what do we don't know, and all these things we know, right? And then we look into what we were asked to find, right? If we were asked to find work, maybe we need to find the specific volumes at state 1 and 2 in a given process. So then we know that we need to find these parameters. So we need to know all the knowns and also how to find the unknown parameters that is instrumental in solving this given question, right? And then after finding the necessary states, we can go to step 4, to write down the first law and eliminate the terms that are not applicable to selected control mass or selected process, right? If it is an adiabatic process, there's no point of considering heat heat transfer, right? If it is an isothermal process, the internal energy is not going to change. So likewise, so we can keep on things like that in our head, and then we can move forward. And then as necessary, we can combine the first law with ideal gas law or the property tables, depending on the conditions of the substance, to find the missing parameters or the other required components of a given question, right? So this is a summary of solution process that we can use. And now I want all of you to try this question. Please try this example 1, take 5 minutes and try to solve it, and we'll discuss it in 5 minutes altogether. Perfect. So this question is about a piston cylinder mechanism that contains 1.5 kilograms of water at given pressure and temperature, right? So if I were to draw the piston cylinder mechanism, so it's right here, and then I have a piston inside this setup. So this is the piston, and then in addition to that we have a spring that is adding force on the piston, right? So there inside the chamber we have water. Inside the chamber we have water. And what are the details of this system? So this is state 1. At state 1 we have m equals 1.5 kilograms, and then p equals 200 kilopascals, and temperature equals 150 Celsius, right? And then in state 2 we have the same setup, and we have the spring and the piston, and the state information is given as well. Again, inside the cylinder there's the substance water, and pressure is given as this is P1 and P2, sorry, P1 and T1, and now we have P2 equals 600 kilopascals and T2 equals 350 Celsius. What can we say about the mass in the state 1 and 2? Is it going to be the same or different? It is going to be the same, right? Because this is a closed system. This is a piston cylinder mechanism which does not allow the mass to flow out. So m is going to be the same value, 1.5 kilograms. Okay, now the question asks us to find the final volume, work done, and heat transfer during the process, right? To find the final volume, we have to go to the property tables. We have been provided with the pressure and temperature, so it should not be a challenging task, right? So as usual, we go to property tables with our temperature and pressure. So our pressure is 600, temperature is 350. So we can either start with temperature or pressure entry tables. We'll type water. Saturated water. Okay, so we found the temperature entry table first, so we'll start with that one, and we'll try to find the we'll try to find our temperature, which is 350 Celsius, right? There we go. Saturated water, 350 Celsius. Here we go. We have 350 Celsius at this point, right? And then our pressure was 600 kilopascal, right? Then the saturation pressure, the second column is the saturation pressure of this given substance. So saturated water, and the pressure is given in kilopascals. So if we think, if we draw our PV diagram here, and this is our dome. And if we draw a isothermal line, it's going to be like this. And the temperature here is 350 Celsius. And then there we can check the saturation pressure. It is given as 16,000 kilopascals, right? And our pressure is what? It is 200 kilopascals. What can you say about our pressure? It is definitely less than 16,000 kilopascals because we have 200 kilopascals, right? So then looking at this, what can you say about the state? What can you say about the state of our substance? This is 200 kilopascals, right? So where did I get 16,000? So 16,000 is from here. This is 16,500 something. So I just put 16,000 here, roughly. Right? You can grab that value. Okay. What can you say about the state of our substance? Is it compressed liquid, superheated, or in two-phase region? Anybody? It is definitely in superheated. Excellent, George. Excellent, Scott. So like we get this intersection point. So there's the point where our pressure and temperature is available, right? So the substance can exist in this temperature and pressure only in superheated region. Therefore, now we know that it is not in two-phase region. It's definitely in superheated region. Now we have to go back to superheated tables. So I will use the same search saturated water, superheated water. Now we'll zoom in, and our pressure of interest is 200 kilopascals, right? So let me quickly try to find 200 kilopascals. It's right below here, 200 kilopascals. And now we need to find our temperature. It was 350, right? So let me quickly check that one. No, it was 150. Sorry. No. Sorry, in the previous explanation, I checked 350 Celsius and 200 kilopascals, which is wrong because the state 2 is the one that we are interested in. It was 350 Celsius and 600 kilopascals, right? Still, that is in superheated region because we don't have the pressure that we have here is less than the saturation pressure. 16,000. 600 is also less than 16,000. Do I make sense? Do you guys understand what I mentioned? Because I accidentally picked 200 kilopascals as the pressure. It was wrong. Like we should have checked 600 kilopascals, but the decision would have been the same, right? The same procedure. Okay. So if you don't understand or if you have any question, confusion, no. We cannot use state 1 or 2 to find the properties of state 2. We have to use state 2 parameters. What I tried to mention is like when we draw our PV diagram, there we had what? Anyways, so our isothermal line. So this was 350 Celsius isothermal line, and we had our saturation pressure around 60,000. And if we had, oh, this does not allow me to change the color. Okay, now it's good. If we had our pressure as 600 kilopascals, we'll be meeting it in the superheated region. Therefore, we should look into superheated region, right? So the pressure should be 600 kilopascals, not 200 when for this state. Okay. Now we'll try to find 600 and 350 Celsius. No, there's no order for finding states, George. Like you can either start with 1 or 2. It doesn't matter really. Perfect. Now let's go back to our discussion. So we'll not be looking at 200. We should be looking at 600 instead, right? Because that is the pressure that we should be looking at. And we find our 600 kilopascals here, and 350 Celsius is here. So now the third column, you see that the third column here, this is the enthalpy column, this is internal energy, and the first column is what we are interested in as of now, specific volume, right? So specific volume at this point is 0.47424, right? This is the specific volume at this point. Everybody clear about how we did that? Okay. And then in this question, the question asks us about the final volume, right? Now we have our V2 value found from the table, and to find the final volume, we can multiply this final volume, specific volume, by the mass of the system, which is 1.5 to 1.5 kilograms, right? And then after finding the final volume, the question asks us to find the work, right? To find the work, we can use the known relationship P delta V, right? So how do we use this equation? Like the integral of P dV, right? In order for us to use this one, we need to know the specific volume at state 1 as well, right? And then we can find, if we know these two, we can go and find the work. And then the question asks the heat transfer, right? It is very important to know that heat transfer, unless given in the question, it's not easy to find from the property tables. Not easy means we cannot find the heat from the property tables. So in our first law, of delta U equals Q12 minus W12, right? So we already found W12, right? I mean, we have not calculated it, but we have found a way to calculate W12. But we do not have a way to calculate Q12 as of now. Do we have a way to find delta U during the process? Do we know a way to do that? Anybody? How to find delta U or internal energy change during this process? Excellent. So we find U2 and U1 from property tables, and then we can find delta U as well. So if we find W12 and delta U, then we can find the heat transfer during the process, right? So when we are grabbing the properties for specific volume, we should grab the properties for internal energy as well. So now you remember for V2, we found the specific volume to be this number, and right adjacent to it, we had the internal energy. So we already found these two, right? And can you try and find V1 and U1? These two, can you try to find that one? Please find these two from property tables. Try and see whether you can identify the state of the substance at this condition, the initial condition, and whether it's saturated, whether it's in saturated region or whether it's in superheated region, and use the appropriate table and see whether you can come to this number. So state 1 is 200 kilopascals and 150 Celsius. This is state 1, right? take 2 minutes and try to find this one. If anybody already have found this one, please let me know, and if you had any challenges or not. Okay, perfect. So everybody finding it good? Like you can find V1 and U1 as well from the tables. Perfect. Now, after you found V1 and U1 and V2 and U2, you can calculate the final volume without a doubt, right? So it's just a matter of multiplying the specific volume at state 2 by internal energy. And it is interesting to see the specific volume at state 1 is higher than state 2, right? So even when I tried solving this problem firsthand, I was wondering why the volume was reducing, because the catch is there's a spring load. The spring should have been loaded at the initial state, and then it have also inserted more work into the system. So a spring should have done work on the system in order for us to see this phenomenon, right? So this direction on the process curve. Do it make sense? Okay, perfect. Now is this curve, now we can mark the process curve, right? So is this curve a straight line or a curved line? It is straight. Excellent. Because this is a spring loaded system. We learned that the force and distance relationship, or the pressure and specific volume relationship of a spring loaded piston cylinder mechanism is going to be linear, right? Therefore this is going to be a straight line. If you don't remember this discussion, you can always go back to the previous lecture recording and check that one. So we agreed that this variation is going to be linear. How it is going to be linear, we derived it in the previous lecture. Okay, so once we know this is linear, then this is a trapezoid, right? So now it is a piece of cake. To find the work done during the process, what we need to know is initial pressure and final pressure is already given, and initial volume and final volume, we know that. We just have to find the area of this trapezoid, and there's a catch here. Is it going to be positive or negative? Area is going to be area anyways. Should we put a positive sign or negative sign? Has the work being done on the system, or the system has done work? Desa is right. So the work is done on the system, because when a substance is contracting, that means the work is done on the substance. If the substance is expanding, then the substance has done the work, right? So if you find this challenging at any point, to find this distance between these 2 points, always use V2 minus V1, right? Then you will see the final volume compared to final volume. If the initial volume is larger, that means system contracted, so you get a negative sign. If compared to the initial volume, the final volume is larger, V2 minus V1 is going to be positive. That means the system did work, right? So you can do that way, or you can just remember by contracting. If the system is contracting, then the work is done on the system. If the system is expanding, then the system is doing work. Perfect. Now, so when you are calculating the work, in addition to the area of the trapezoid, we have M, the mass of the system as well, right? So if we did not know the mass of the system, then what we would have done is calculating the specific work, right? Work done per unit mass of substance. But in this case, we know the mass, therefore we can add it. So we get the answer in kilojoules. And
importantly, we have a minus sign here, right? So the work is being done on the system. And here, if we did not have the mass and we use the area, then what would be the unit that we are getting for the answer? The unit. If we did not have the mass and if we did not multiply by the mass, it's going to be kilojoules per sorry, kilogram, right? Because it's per unit mass, right? The work done per unit mass. In this case, we multiplied by the mass, therefore it's just the total work done by the substance or the system, right? Now it's the next step is easy. So we found the internal energies, therefore to find the delta U, we can multiply our internal energy values by the mass of the substance, and then we already found the work, therefore it's just a matter of substituting. And if we take the Q12 term into one side, then the equation would look like this, and when we substitute the internal energies, it's fine. And then you importantly should substitute the work with the sign as well, right? The negative sign, that is very important, because we have the plus W12, but our W12 value is negative 291. So we substitute negative 291 here plus negative 291 within brackets, right? And you arrive at the answer. Are we clear about this one? How we substitute values here? Perfect. Now, if we did not know the mass of the system, then in the previous step, what we would have calculated is specific work, right? And then we'll substitute specific internal energy values and no mass, because we did not know, if we did not know, right? And then what we would get for the heat transfer is a specific heat transfer per unit mass of substance. And then what is going to be our unit of the heat transfer? Now we have got kilojoules, right? We have got kilojoules now. But if we did not use mass in the calculations, then what we are going to get? What are we going to get? Any ideas? I'm asking for the unit if we did not use the mass in the calculations. So if we did not know the mass, then our equation would look like Q12, the specific heat transfer, specific heat transfer equals U2 minus U1 plus simple W12, right? So this is the specific form of the thing. If the mass was not provided, this will be the one that we are using. So any idea what is going to be the unit of our final answer? It's specific heat, right? It's the same thing, specific heat, kilojoules per kilogram, right? Are we all clear? So this is the equation. What will be the equation of work? Okay, so if we did not have mass, then we will not use this one, and then it will be just other components. So then you have specific volume here, and then you get the specific work. Did I answer you, Menna? Okay, so okay. Now, moving on to the next example, try and solve this question. Take 5 minutes of your time and try to see if there's any challenging points here. So in this question, The piston cylinder mechanism is already drawn. So drawing the physical system, it has been done for us. Therefore, it's easy. And a piston cylinder mechanism contains 2 kilograms of liquid water at 20 Celsius. So the first state is given, right? It's liquid water. So we don't have to worry. If it was just water, then we have to check the state, right? So 2 kilograms of liquid water, the initial state. State 1, M equals 2 kilograms, and then temperature T1 equals 20 Celsius, and P1 equals 300 kilopascals, right? So in this case, it is the state is liquid. Now at state 2, the pressure is given. T2 is not given. P2 is given to be 3 megapascals, and V2 given. V2 equals 0.1 cubic meters. Can we use this total volume in the property tables to find the state and whatnot? Can we do that? Anybody? Any idea? Perfect. You're right, Scott. We need the specific volume, right? So we calculate the specific volume at state 2 because we cannot take the total volume to the property tables. So to find the specific volume, we know that the system mass is 2 kilograms, then 0.1 divided by 2, which is going to be 0.05, right? Now this 0.05 value, we can bring that to the property tables, right? And in the state 1, we have not been provided with specific volume or the total volume. Neither of these has been provided. So now the question asks us to find the final temperature. So finding the temperature, this is a task, right? We need to find that one. And then show the PV diagram. Okay, show the PV diagram. Draw it. Okay. Find the work done during the process, work in the process, right? So we are asked to find W12, and there, if we were to find the final work, then we know that we need to know the volume terms, right? So V1, V2 is already known, but V1 is not known. Therefore, we need to find this one and temperature in order for us to solve this thing, right? Any questions so far? Okay, I see none. And let's start with state 1. How to find V1? You remember, for a compressed liquid, we say that we disregard the pressure at that given point, but we consider the temperature and then look for the relevant Vf value, right? Therefore, we know that what we are looking for is Vf at 20 Celsius. Right? Agreement there. So we need to look for Vf at 20 Celsius. Yes or no? Okay. So I know that some of you may be already busy with the workings of the question, but like when we are discussing, please be involved in the discussion because you have many questions that you can solve by yourselves. So in this class, it's the purpose is to like discuss, right? Therefore, be involved in the discussion. So now we have 20 Celsius. So now we go to tables, and there we start with the saturated tables because we need the VF value, and we search for water, and then we arrive at saturated water and 20 Celsius and VF 0.001002. So this is what we are interested in. So we get 0.001002 cubic meters per kilogram, right? So we already found that one now. So we have our specific volume at state 1. And for safety, I would always try to pick U1 as well in an exam situation because I don't want to find the state again. Like recording a value from this one and noting UF is 83.94. That is easy than trying to find the state again, right? So that is going to be, what is the number? 83.94. 83.94 kilojoules per kilogram. This was not in our solution plan to find the UF. We just recorded that value in case if we need it, right? So now we want to find the temperature at state 2. Right? We start with saturated tables, and the pressure given is 3 megapascals. Okay, now let's go, and we want to compare our specific volume at this 3 megapascal state to see whether it's in saturated state or compressed liquid state or in superheated state. Okay, now we go there and we go for the pressure entry table. And the megapascal means 3000 kilopascals, right? 3 megapascals mean 3000 kilopascals. Now saturated water, pressure entry. Now we found 3000. This is the set of properties for 3000 kilopascals or 3 megapascals. And there VF and VG values are in the third and fifth columns. So our specific volume value, we know that it was 0.05, right? So what can you say about our state by looking at these specific volumes and our given conditions? Excellent. So it is in two-phase region, right? Because ours was 0.05 and definitely 0.05 is less than 0.06 and higher than 0.01001, right? Therefore, we know that this is in two-phase region. So now to find the temperature at state 2, it's very easy. And we know that it is 233.9 Celsius. So state 3 temperature 233.9 Celsius. Okay. Now we know that, and we know that it's a two-phase mixture. And what else do we need? Find the final temperature. Done. And we need to draw the PV diagram, right? So now when we go there to draw the PV diagram, we start with V1. V1 was found to be 0.001 and V2 was 0.05. So this is an expansion process. The volume has increased. Therefore, our V1 is here and V2 is going to be here. And then we mark it like this, the process, right? As we see here. When you are marking the process in an exam, so please mark the arrow of, to indicate the direction, right? Even in the solution, we have not indicated the arrow. So please do mark the arrow. Mark the initial state, mark the final state, and mark V1, V2, and P1, P2, and then mark the process direction. Now we have found the temperature, indicated it in the PV diagram, and importantly, the first point was out of the dome because it was in the compressed liquid region, right? And then the second point is inside the dome. So locating your points in the appropriate regions is another important thing. Otherwise, you will lose some marks for that. Okay. And to find the work done during the process, we can use this equation to find the area of a trapezoid. So here it's the total volume that you see here. We can use total volume, or we can use specific volume and multiply it by the mass as well. So we can either write this one as well, P1 plus P2 into M into V2, sorry, to right. So we could have used either of these equations and arrive at this final answer. So final answer, the units are very important. If you do not use the units, you will be communicating something very wrong to another engineer or another person. If you say that the work done per unit mass is 161, that's a different story. The total work done during the process is 161 kilojoules, that is a different story. Therefore, it's very important that we pick the right units. Okay. So any questions so far? We solved the question 2. So okay, so at state 1 it says liquid water, right? So if you are not sure whether it's liquid water, definitely you can take the state parameters 20 Celsius and 300 kilopascals, and you can start with saturated water temperature tables, and then you go there and then you browse 20 Celsius, right? So this is going to be your saturation pressure, and then you can try and draw a PV diagram in this case, and this is the dome, and you could try to draw an isothermal line. So isothermal line for 20 Celsius, right? Our interested pressure is 300 kilopascals, and the saturation pressure is this value. So definitely 300 is somewhere here. So we can make sure that it is in compressed liquid region. And then you can get the VVF value as well, right? But in the question it said liquid water, so we directly assumed it is in compressed liquid region. If you are not sure, you can always go and check using the basic principles that we already know. Okay. Any other questions? Anything not clear about the solution process? It's very good that you ask questions, right? I mean, that is how we all learn. Sometimes when I am in a class, if I do not ask questions, when another student asks a question, then I see, oh, even I did not understand this part, right? So that's why it's important that you all involve and ask questions and be engaged in the lesson. Okay, are we all good with this one? Or do we have any more questions? guys, please be involved in the discussion. Like if you are good, then say yes. Like if you understood, like it's very simple, right? You either understand it or you don't understand it. It's not rocket science. Please put something in the chat so that we can move forward, right? Yeah, like it is straight from 1 to 2. It comes from the, as it is linked with a spring, right? So when we load a piston with a spring, in the last lecture derived that it's going to, the volume and pressure is going to vary in a linear relationship. So Dazer isn't the area for triangle is wrong, but the thing is this is not a triangle, this is a trapezoid. So this is the area that we are talking about. So area of triangle, if you use this expression for an area of a triangle, that will be wrong, but this is the area for a trapezoid, so this is right. Okay. Okay, then let's move on to the next one. So in this question, the good thing about this one is it states the state, right? It says, clearly says it is at superheated state at the beginning. So a cylinder fitted with a frictionless piston contains 5 kilograms of superheated R134A. So this is another common mistake that students do. So don't assume that everything is water, right? So it is not always water. There are some other substance in the world as well. So check whether it's the water or some other substance, right? So now this one has R134A and the pressure at state 1, P1 is given as 1000 kilopascals and T1 is given as 140 sorry 140 Celsius. Okay, and now the setup is cooled, right? The setup is cooled at a constant pressure until the refrigerant reaches 25% quality. Now it is being cooled and pressure is a constant pressure in the constant pressure process is not going to change. Therefore we can say that P2 equals 1000 kilopascals again, and X is given to be 0.25 and now okay, these are the information that we have. By looking at state 2, what can we say? Is it in saturated region or like two-phase region, or is it in superheated region or in compressed liquid region? Can we say anything? State 2, anybody? It is two-phase, right? Because there's a quality defined. If it is outside the two-phase region, then it is not, the quality would not be defined, right? So find the work done in the process, right? So now we know that if we try to draw the PV diagram, so this is the dome, and the question says to us that it was at superheated region. So this is state 1, V1, and now it is inside the two-phase region, right? So by looking at this, we know that the process is going to be like this, because the pressure is constant, therefore it's going to be a horizontal line parallel to x-axis. Therefore we have a process like this, and it is going to be from 1 to 2, right? The area that indicates the work done is going to be this one, so we are interested in finding this one. So in order for us to find this, the pressure is already there. To find we need to find the area, so the pressure is already given, so we have to worry about the specific volume at state 1 and state 2, right? Those are not given. The system mass is also given, therefore we can find the total work, not the specific work. So in order for us to find the state, we can go to superheated tables at state 1 and try to locate this point, right? How do you know the arrow is pointing from right to left? Because state 1 was at superheated region and state 2 is inside the dome. So the process is done from state 1 to 2. So we know that the arrow is directed from 1 to 2, right? Awesome. So now, we have to go to property tables and look for 1000 kilopascals and 140 Celsius at superheated conditions for R134A, right? So I go to my property tables and type R-134 and wait, give me 1 second. Okay, R-134. Now saturated tables are popping up, but I am interested in superheated as of now. So my pressure of interest is 1000 kilopascals and temperature is 140. So I'm going to look for 1000 kilopascals. I'll scroll down until I find 1000 kilopascals. I scroll down further. Here we go. We have 1000 now, and the temperature was 140. And 1000 and 140, it's right here, 140 Celsius. Okay, let me use another color. Okay, now we have 140 and 1000 is right here. What we are interested in is specific volume. We can directly grab that from here, right? Any issues so far, or are we good with that one? How we found the state at state 1 specific volume? Perfect. Now for state 2, we know that it is in two-phase region, right? So there we have the pressure given, so we need to find 1000 kilopascals. Now we'll go to the property tables and we'll try to find the saturated tables for R134A. Saturated R134 is here, and the important thing to note here is for every substance that we have, we don't have pressure and temperature entry tables, right? It was only for water, as water is being used frequently in the calculation. Therefore, we have to deal with what we have here. Like for R134A, we just have temperature entry tables. Otherwise, we just would have picked the pressure entry and located 1000, right? But unfortunately, we don't have that luxury here. So now we have to locate the appropriate bracket that contains the pressure. Okay, now look at this one, and you know that 1000 is between 887 and 1017. So this pressure bracket definitely contain our 1000 kilopascal value, right? Everybody agree? Anybody having doubts about that? Okay, so now after that point, we need to find the specific volume, right? That is what we are interested in. So in order for us to find the specific volume of a mixture, we need to find Vf and Vg both, right? So we have two ways of doing this. We can interpolate for our Vf value at 1000 first and Vfg value at 1000 first, and then use these things to calculate our final specific volume, right? So we can find our final specific volume at 1000 as Vf at 1000 plus X already known and Vfg at again 1000, right? So we could have either done that, or we could find our average specific volume at the given quality and in this condition, and average specific volume at this condition, and then we can interpolate to find the average specific volume at 1000. You know what I mean? So like there are two approaches that we could take. So either works. That's what I'm trying to say. Okay, let's go to the solution here. So this is what I was telling. So at 1070, for this given quality, we can find the specific volume like this, right? We get the VF at 1017, and we get the X that is provided in the example, that is 0.25, and then we get VFG at 1017, and we calculate the average specific volume at 1017, right? Similarly, we can calculate the average specific volume at 887 kilopascals. We take the VF value there, and we get the X and VFG here for that particular pressure, and then we get the average specific volume at that condition. Now we have two specific volume values under these given conditions. What we are interested in finding, is finding the average specific volume at 1000. So we can get these two values and then use the pressure values as X values and specific volumes as Y values, and substitute in our interpolation equation to find our final answer is this one, right? In this solution, the 0.871 is the average VF value, interpolated VF value at 1000, the first approach that we discussed, VF 1000, and this is VFG 1000. So in this solution manual, I have provided you with two approaches that you can go with, right? Either you can find the average conditions already for 1017 and 887 and then interpolate, or you can interpolate for VF and VFG at 1000 from the known values and then calculate the average specific volume at that given condition using the quality given. Am I making sense? Anybody having questions? Right. So now, okay. So please do try to calculate this one yourself so that you understand perfectly you got it right. Okay. So that you would not come across any difficulties in the exam. Okay. Now, after knowing the volumes, the calculating the work is pretty straightforward, and in this one it's a rectangle, so not a rectangle, yeah, it's a rectangle, yeah. So we can get MP into V2 minus V1, right? So there you substitute mass and pressure and two specific volumes and get the final work. Where did we get 0.0? This is VFG. Let me quickly explain this to you. This is VF value at 1000. Okay. Okay, the colors are going out of selection. What can we use? Okay, maybe just black. This is VF at this given pressure, and this is VFG at this given pressure, and again this is VF at the given pressure, and this is VFG. Did I answer you, Menno? That makes sense? Awesome. So any questions so far? What is X? X is the quality, which is given as 25% here. Okay. Okay, so how we got us the interpolated specific volume? Sure, we can do that. So we have two v values here. So we can agree that this is, we can pick that to be y1 and this is to be y0. So, and y is, this is y, and this is x1, and this is x0, and this is x. Okay, what we do is we pick these values and then substitute in this equation. So what we are interested in finding is y. We can put it there. Y is going to be our specific volume at state 2. Y0 is going to be 0.00642, 0.00642, and plus y1 is going to be 0.00566 minus, and y0 is going to be again 0.00642, close the bracket, and multiply it by x minus, x is 1000 minus x naught, which is 887 divided by x1, which is 1017 minus x naught, 887. So if you solve this equation, then you will get your final specific volume. Did I make sense, Jacob? Perfect. Okay. And now the last question of the day. So let's try to quickly hash that down. Please take your property tables, and this is something you know already. Please try to identify these properties. So you remember for enthalpy also we have the same relationship, right? You can compare the enthalpy value you have with HF and HG and determine whether it's in two-phase region or superheated region or compressed liquid region. So it's the same idea as internal energy or specific volume. So you can discuss the answers at this point. I don't have answer key for this one. So you have many questions with the answer keys in the assignment 1 and 2. So you can check for the answer keys there. We can discuss this in the class right now. Okay. Okay. For state 1, the substance that we are interested in is R134A, right? The parameter that we have is enthalpy. So now we need to find the state and other parameters, pressure, internal energy, quality, right? So let's take our enthalpy and go to property tables and try to find R134A, and we are already there. And the pressure, no, temperature given is 40 Celsius, right? So now the interested state is here. It is 40 Celsius. And importantly, this table does not have the enthalpy value. So in an exam situation, don't panic. So just scroll down. There should be another table that has the enthalpy values, right? Here you see that now we have enthalpy. So for every substance, you have enthalpy and all these parameters. So if you don't see it in the current table, don't panic, just scroll down, right? So now 40 Celsius, we draw this line. Now there our enthalpy value was 426. So 426. Now we look at HF and HG. Sorry. Right. So HF and HG. Right. So by looking at these two values, what can we say about the state of this substance? It is superheated, right? Excellent. Because this one is 426 and 426 is higher than our Hg value. So that means we have to go for superheated tables, right? So we again look for superheated tables now and saturated superheated tables. Okay. Now we have to find our 426 for this given temperature, right? Now at 40 Celsius, we look for our enthalpy value. It is 437 at 50 kilopascals, and it is 437.22 at 100 kilopascals. So our interested value is 426. Now we have to find 426 at 40 Celsius, right? So again, we check for this temperature. It is 40 Celsius, 150 kilopascal, but we get 436. But we are interested in 426. It is not even close here, right? So we browse down, and so let's check here at 40 Celsius. This is 430, and this is 428, right? So now at 600 kilopascal, we got something closer, right? 428.88. And let's say for 800, so now we got 424. So Dazer is right. Excellent. So now we found the bracket, right? The enthalpy value that we have, enthalpy and pressure, right? And the other parameter we are interested in is internal energy, right? So this is what we need to find. And we know that our enthalpy, given enthalpy value is 426, right? And at 800 kilopascal pressure, we have 424.86, right, as our enthalpy value. And then at 6, and we can grab the internal energy real quick as well, 403.17. So, right. And now at 600 kilopascals, we have 428.88 as our enthalpy value. 428.88, right? And the pressure is 600. And the internal energy value, let's grab that one as well. So internal energy value is given in this column. So it is 406.11. So 406.11. Okay, now we need to find the pressure and internal energy. Okay, so in order for us to do this, this is a matter of interpolation now, right? So we can get this information into our question and start our solution process, right? Copy. Can we paste it here? Nope, we cannot paste it, but we have it right here by the side, right? Can somebody interpolate for pressure and say, tell me what is the pressure value for this question. So 743.28. So everybody is getting that one. Okay, so then according to your friends, the pressure is going to be 473 point, no, 743, sorry, 743.28 kilopascals. And internal energy, anybody calculated the internal energy for this one? Okay, so 404 kilojoules per kilogram. As many of you are getting the same thing, I believe all of you are doing the right interpolation process. As we discussed earlier, it's simple as we demonstrated in the previous example. And now, what is the quality of this one? Anybody? It is non-applicable because this is superheated, right? Excellent. So it does not have anything to do with. And then this is superheated region, right? The phase. And now we saw the first part, and then in the second part, what do we have here? In the second part, we have been provided with the pressure, right? And then we have been provided with the quality. Now, what does that say about the phase? It is two phase, right? So we can say that two phase. Now, this makes our lives easier because like we don't have to look for the superheated tables or saturated, and we don't have to worry about that. We know that it is exactly saturated tables. We don't have the ambiguity of which table to use, right? So now we need to find temperature. So like we go to tables and we need to locate, we try to locate 500 kilopascals for what? R410A. So very important, R410A. So the substance, right? So this is a common mistake when you are dealing with one substance. Then you down in the road, maybe you will be using the same table in an exam situation under the pressure. Please be attentive to the material or substance. So now it's R410. We'll go and I will search R410, right? So we'll go for R410 tables and saturated tables for R410. And our pressure of interest is 500 kilopascals, right? So now for this one, 500 kilopascals, where can we find it? So 500 is somewhere between, sorry, somewhere between these two numbers, right? So in this case, you remember how we did calculate the found the specific volume and internal energy for this kind of a situation in the previous question. So this at this point at minus 15 and 480 kilopascals, so the pressure is 480. $480.4 is the upper bound of the pressure, and we are interested in knowing 500, what's happening at 500 kilopascals, and the other number given here is 573.1, right? And pressure is there, so you can find the average internal energy. So UF is 35.08 at 480. So 35.08 into plus 0.5, which is the quality, into UFG. UFG is 212.79. 200. So let me write it in a concise manner. This pen is giving me hard times for some reason. 8 plus 0.5 into 212.79, right? Likewise, you can calculate the average specific volume for this pressure, and then we can interpolate to find the specific volume that we needed. Or this is not specific volume, sorry, my bad. This is internal energy, right? You can use this same pattern to find the average specific volume at this state, and then we can interpolate to find this one. Can somebody do the calculation for me? Like anybody who's willing to do this? So at this point it is 146, and here what is it? What is the number? Can somebody do the calculation there? 141.475. And in order for us to do the interpolation, let's go back to the slide. Let's take a screenshot of this one, and then go. You also can take a screenshot of this one so that you have that one available for you while we are doing the calculation, right? And then let's do this. So for different pressures, like we got values. So P equals 480.4, 500, and 573.1. 480.4, 500, and 470. No, sorry. 573.1. Right? This is pressure. And then we have our U values, which we got as 141.475, 141.475, and now we have the bottom one, 146. 146. That's our U value, right? So now we need to do the interpolation. So let's try and do that. Here, you know that the slope of two things, like you can get the equation from the previous slide. So for interpolation, you can say y equals y naught plus y1 minus y naught into x minus x naught divided by x1 minus x naught, right? So let's go there. Y equals y naught plus y1 minus y naught into x minus x naught divided by x1 minus x naught, right? So this is the equation we had from the previous one, and then we can substitute the values. Y naught is the one that we are interested in, the parameters. Y naught is going to be this one, and y1 is going to be this one, and this is the y we are interested in, and this is x naught, x, x1. So it doesn't really hurt you if you change the x1, interchange x1 and x naught, okay? And I mean, what is important is you pick x0, y0 in the same row. So in another scenario, you could have used this as x1 and y1, so, and this one as y1, and this one as x0, and this one as y0. So if you use the convention that we use in red color or blue color, it doesn't really make a difference to your final answer. You can try that and see whether it really makes a difference, but it does not. Okay. So Alan got the answer as 36.6 as after solving this one. Are we all getting the same answer? Yeah, like so, Alan, you got it mostly right. So yeah, so for compressed liquids, we get the properties at that given temperature, UF values at that given temperature, which is UF, that is true, as the property. We assume that to be close enough, right? So, and then for two-phase region, if the quality is given, we know that UF plus XUFG is going to be our answer. That is correct. And in saturated vapor region, there's no such thing as U gas. It is internal energy in saturated vapor region. It is UG is on the line, right? So UG means the values on the saturated vapor line. So in superheated region, we have internal energy values for that. Did I answer you, Alan? Okay. So UG is not always equal to the internal energy values that we have in saturated, no, we have in superheated vapor region. Okay. Okay. So now we have the answer. This is not the answer, and it is not practical to have 36 as well, because it should be somewhere between 141 and 146. Therefore, the answer should be 142.775. Perfect. So that is how we calculate. You can use the same procedure to find H as well, right? Very same procedure. You will go to these two pressures and then you locate your enthalpy values and then do the same interpolation. Okay. Can we finish the table and get T and H quickly? So we can, like, you can get the temperature values for these two as well. Again, so now we have calculated U, therefore we can forget about U now, and then we can start with temperatures. Right, so now we'll pick the temperatures. We'll pick the temperatures at 480.4. What is the temperature? Let's go and check. Let's go up, and the temperature is -15 and -10. It's a bracket, so we pick -15 and -10 at 480. It is, yeah, so -15 and -10, and this is the temperature that we are interested in. So then again, for the similar to previous case, this becomes like, let's say in red assignment, like we'll get rid of these ones for now, and y0, and this becomes y, and this becomes y1. You can substitute the y1, y0, and y values in the interpolation equation, and then you get the temperature value here. If you want to solve, then you can get the answer there.